The colonization of the Milky Way, the movement of stars and the flying of spacecraft, hopping from star to star and colonizing alien planets, expanding throughout the galaxy until the entire Milky Way is populated. It all sounds quite simple. Yet, if all of this is supposed to be so effortless, we must ask ourselves, where are the aliens? And why has no one yet colonized the solar system? This is the question Enrico Fermi posed, which is also crucial in considering the Great Filter. However, today we will only touch upon this topic briefly. Instead, we shall explore how our civilization or potentially other intelligent beings in the Milky Way might expand within the galaxy. When we think of Star Trek, Star Wars, or other science fiction series, we envision spaceship occupants of all sorts traversing with technology indistinguishable from magic, moving through ominous folds of space-time and achieving speeds that are both thrilling and terrifying. Yet, warp drives and similar concepts are not relativistic velocities, but rather physical sleights of hand meant to make us believe that we might someday effortlessly leap to the stars. In reality, that is not the case. So, what methods remain for us to travel to the stars? How might extraterrestrials, or we, succeed in leaving our solar habitat and become a galactic species, one that spreads across the entire Milky Way? Well, physicists have examined this and found that the galaxy could be colonized relatively swiftly, within just a few million years. And the twist is, entirely without the physical tricks that science fiction authors conjure. But how is this to be accomplished? How are intelligent civilizations supposed to populate the Milky Way with relativistic drives if spacecraft can only achieve speeds below the speed of light? That, my dear viewers, is what we shall investigate today as we delve deeply into the concept of star hopping. That is, well, hopping from star to star with minimal effort, without faster-than-light drives or other such hocus-pocus. What does star hopping entail? How might humanity accomplish it? And what methods are necessary? Join me today as we explore together the most simple method to colonize our galaxy. The exploration of potential habitats for extraterrestrial civilizations may seem akin to searching for a needle in a haystack, while the haystack is ablaze and we are wearing gloves. This is an analogy I used in some of my other videos, yet it simultaneously presents one of the most philosophically and astronomically important and demanding endeavors. Broadly, this pursuit encompasses two primary approaches: direct and indirect detection. These two methods offer distinct pathways to discover and confirm the existence of intelligent life forms beyond Earth. Direct detection entails finding physical evidence of extraterrestrial visits, such as artifacts or other indications of their presence on Earth or within our solar system. This method, however, is exceedingly challenging as such evidence either does not exist, has remained undiscovered, or we lack the appropriate technology to detect these artifacts, or they are simply exceptionally well hidden. Direct detection, therefore, means discovering unmistakable signs of extraterrestrial beings within our local spacetime, for example, within the solar system, indicating that they visited Earth thousands of years or millions of years ago. On the other hand, indirect detection focuses on the search of technosignatures. These signatures could be electromagnetic signals, such as radio waves emitted by advanced technologies. However, we must not overlook the physicist who specifically researched this topic, Michael Hart. His Fact A is a central point in the discussion surrounding the Fermi paradox. Hart formulated his argument based on the observation that there is no evidence of extraterrestrial visitors on Earth. For him, this implied that no other technologically advanced cultures exist or have ever existed in our galaxy, because such a culture with the capability for interstellar travel would have eventually visited Earth. Since this is evidently not the case, Hart concluded that we might be the only technologically proficient beings in the Milky Way. This conclusion is based on the assumption that an advanced civilization, if it existed, would have either left direct traces through visits to Earth, or at least sent indirect hints like technological signals or artifacts, those very direct or indirect indications that astronomers so eagerly hope for. Whatever the reasons might be, we cannot ascertain here. Such speculation could take us too far afield. Therefore, we will set aside the sociological aspects of such a discussion. Why aliens would travel interstellar distances or why they would not lies outside our experiential horizon. However, do aliens necessarily need incredibly advanced technology to spread across the galaxy? What if a civilization uses rather simple methods to expand, leveraging the movement of stars through the galaxy to proceed forward? Let us explore in the next chapter how star hopping could be employed to colonize a galaxy. The notion that civilizations in the Milky Way could spread without relying on highly advanced technologies like warp drives is both a fascinating and question-provoking concept. Some scientists even argue that it would be feasible within a relatively short time frame at sublight speeds. Spaceships wouldn't need to travel incredibly fast. Even at just a fraction of the speed of light, significant progress in the colonization of the Milky Way could be achieved within hundreds of thousands of years. This time span may seem enormous by human standards, but in the cosmic context, it is relatively brief. Moreover, such civilizations wouldn't require continuous technological advancements. Only the ability to establish stable and reproducible settlements. This could be accomplished with colony ships that travel over generations to settle new worlds. Yet, let us take a step back and not put the cart before the horse. This does not mean that civilizations need to do nothing to reach other stars. Of course, vast distances must be traversed. This should not be underestimated. However, one must remember that an expansionist civilization is not the only thing in motion. The stars, which appear to be fixed at the night sky, are also moving. They do so not statically, but follow complex trajectories influenced by the galaxy's gravity. These movements can greatly facilitate the colonization process. This brings us to the concept of star hopping. The idea here is that if a star approaches our solar system, we, as a civilization, simply hop to it without having to undertake significant travel distances. This does not mean that the star would be just a few billion kilometers away from the Sun. That would be a catastrophe and spell the end of most of the planets in the solar system. It would suffice if this star were in the farthest reaches of the solar system, where it could do no harm or alter planetary orbits. Humanity would merely need to board the star, taking advantage of the shortened distance between our Sun and its visitor. Much like a person waiting for a bus steps onto it and is then transported further. From now on, we shall refer to parts of civilizations that move to other stars as sub-civilizations or branch civilizations. On one hand, stars moving towards each other could shorten travel times for interstellar settlers and thus accelerate expansion. On the other hand, the changing positions of stars over long periods could lead to already settled systems becoming isolated as their neighbors move away. This could result in the fragmentation of civilizations into many small, isolated sub-civilizations, complicating communication and resource exchange. All this can be combined with the consideration of the varying speeds of hundreds and thousands of stars, which might be near each other at a given time. The originating civilization would thus have many opportunities to spread, but also numerous dangers if we consider its potential fragmentation. There are various tactics and strategies a civilization can employ to accelerate its expansion and avoid fragmentation. Firstly, it must strategically position itself to harness the natural movements of stars. By placing settlements along the paths of stars moving towards denser stellar regions, galactic societies could optimize and streamline their expansion efforts. This strategy would allow them to reach new settlements without independently traversing vast interstellar distances. However, this requires a profound understanding of galactic dynamics and the ability to undertake long-term planning spanning multiple generations. To illustrate the long-term nature of such planning, consider that stars may take tens of thousands of years to approach each other closely enough for star hopping to become feasible. Thus, civilizations would not only exploit the short distances between stars to expand, but would also leverage the intrinsic motions of their new stellar homes through the Milky Way as vehicles to reach other stars cost-effectively and resource-efficiently, especially those in denser regions. This creates a snowball effect. First, we colonize one star, then from this and our original star, we colonize 2 or 3 more, and so on. We shall call this method the star bus, as it closely resembles a person waiting for a bus and requiring minimal effort to reach their destination. Alongside the strategic advantages of using the star bus, there are also significant challenges. One of the greatest difficulties lies in the unpredictability of stellar movements, such as gravitational interactions with other stars or galactic structures. These events could alter the planned trajectories and present unexpected obstacles. Additionally, civilizations and their branch variants spreading along stellar movements could encounter unknown dangers, such as interstellar matter clouds or high-energy radiation zones. These factors could jeopardize the safety and survival of settlers. Naturally, these civilizations would need to protect their settlements somehow, or, as Carl Sagan described it in his novel Contact, for many civilizations in the universe, they might need to simply hunker down and wait out a supernova or similarly energetic events. These protective measures could involve advanced technologies for monitoring interstellar space and predicting potential threats. Furthermore, these civilizations might develop specialized defense mechanisms to shield their settlements from these hazards. The models which are presented by scientists also consider such unforeseen events and their potential impacts on the long-term stability and expansion of civilizations. When settlers moved to the USA, predominantly pushing from east to west, it was referred to as a settlement frontier. In that case, the continent was already inhabited by indigenous groups, yet the idea that a new group advances into new territory like a wave is known as a settlement or colonization frontier. A crucial element of this expansion would be the speed of this frontier, meaning the rate at which new star systems are colonized. This depends on several factors, including the travel speed of the settlement ships, the frequency of star hopping or star buses, the ability of civilizations to successfully establish and maintain new colonies, the direction of stellar movements, and unforeseen gravitational influences that could divert stars. Consequently, the settlement frontier may accelerate, slow down, stagnate, or even retreat when a new star is colonized, depending on the settlers' encounters with adverse conditions in the new homes. We must also consider the conditions under which a civilization lives when colonizing a new star. It is crucial to acknowledge that societies do not exist indefinitely and may collapse after a certain period for various reasons. Their lifespan can be influenced by factors such as internal conflicts, resource shortages, or external threats. If civilizations only exist for a limited time, colonized systems might remain uninhabited after their decline, leading to a mosaic of inhabited and uninhabited areas in the galaxy. Astronomers who delve into the concepts of star hopping and star buses discuss the likelihood of recolonization, which some regard as quite high. Should a branch of civilization perish, nearby branch civilizations could recolonize the abandoned colony. This recolonization could help maintain the continuity of the settlement front and stabilize the galactic presence of civilizations. In other words, the settlement front would partially turn inwards. To prevent disappearance, sub-civilizations must ensure communication, information exchange, and trade among themselves. These networks could not only facilitate the exchange of resources and information, but also ensure the coordination of settlement missions and support for colonies in distress. A well-connected civilization stands a better chance of long-term survival and continuous advancement of its settlement front. However, we must not overlook that the movement of stars in the dynamics of interstellar travel could lead to significant diffusion effects, which might profoundly influence the colonization of the galaxy and remain beyond the control of even the most advanced societies. These effects would cause branch civilizations to gradually spread throughout the Milky Way, akin to particles dispersing in a fluid. This distribution, however, is uneven and determined by many factors, including the movements of stars, the speed of settlement ships, and the frequency of settlement missions. Stellar movements can lead civilizations to spread along certain paths, leaving other parts of the galaxy uncolonized. This results in a diffuse pattern of colonization, with some regions more densely populated than others. This diffusion effect can cause natural fragmentation of galactic colonization, leading to large uninhabited areas even in a theoretically fully colonized galaxy, as these regions lack the mass or the resources to attract other stars. Over the millennia, a multitude of sub-civilizations would develop. Each of them would possess its own technology and, upon arrival in a star system, would continue to evolve independently. This would result in societies within the Milky Way with varying capabilities. Those with faster spacecraft and superior colonization strategies and technologies could visit areas of the galaxy deemed unreachable by others. Technological advancements such as improved propulsion systems or more sustainable colonization techniques could enable the crossing of greater distances and the colonization of even the most remote star systems. This could mean that branch civilizations with less developed technology remain isolated, while those with more advanced technology might become partially independent of stellar movements within the galaxy. Given the incredible diversity of cultures and value systems on Earth, one can only imagine how distinct the various branch civilizations would be. Some might display a high propensity for expansion and a strong desire for interstellar colonization, allowing them to expand faster and farther than those focused on internal developments. These cultural differences could lead to an uneven colonization of the galaxy, with certain regions dominated by expansive civilizations, while others remain largely uninhabited. Additionally, civilizations might consciously decide to leave certain areas of the galaxy uncolonized for religious, ecological, or strategic reasons. And this is just considering humanity. Who knows what ethical systems extraterrestrial civilizations might have and what their motivations would be. In conclusion, star hopping is anything but simple. It is a highly complex and time-consuming method of galactic colonization, yet significantly easier than traversing the Milky Way with sheer force using massive drives and spacecraft. Most importantly, it is far less energy-intensive and much more efficient. However, such expansion would eventually come to a halt, for although our galaxy contains hundreds of billions of stars, their number is finite. This means that at some point, a galaxy would be fully colonized. Then what? What would the original civilization, the one that initiated the expansion? Or rather, what would the countless branch civilizations do in such a scenario? The Milky Way appears infinite to us. It is no surprise that most astronomers at the dawn of the 20th century believed it encompassed the entire cosmos. They did not anticipate that the universe would be far greater and more expansive than in their wildest dreams. Yet, the galaxy merely seems infinite. The Milky Way, like every entity in the universe, is subject to limitations. There's a finite number of stars and planets, and no inexhaustible reservoir of gas and dust from which new stars and planets can form. Additionally, there's a finite amount of energy. These quantitative constraints apply to all civilizations within the Milky Way. Although the expansion drive of an interstellar star-hopping civilization may appear boundless, it must confront the finiteness and the reality of the Milky Way galaxy. What happens when a civilization reaches its equilibrium? Many astronomers who study the star-hopping model and the consequent colonization of the Milky Way address the concept of the steady-state galaxy, or the galactic equilibrium. This refers to a phase where colonization by spacefaring civilizations has stabilized. It means that some parts of the galaxy remain permanently inhabited, while other regions stay uncolonized. Achieving this state is an exceedingly complex process, dependent on the factors we discussed in the previous chapter. Aspects such as the speed of the settlement front, the movement, trajectory, and position of stars, the movement of a civilization, and its expansion drive theoretically all play a role in reaching galactic equilibrium sooner or later. Another crucial factor in attaining this equilibrium state is the lifespan of civilizations. Even if a society develops the patience to reach other star systems over generations, its ability to permanently colonize these systems is limited by its own longevity. Most models assume that civilizations do not exist indefinitely, but eventually go extinct or withdraw. This temporal limitation means that colonized systems could eventually become uninhabited again, leading to a kind of dynamic equilibrium. In this scenario, the galaxy could exhibit a mix of inhabited and uninhabited systems, with the inhabited ones changing over time. The rate at which new settlements are founded also plays a decisive role. A higher settlement rate leads to faster expansion, while a lower rate favors slower but more stable colonization. It is likely inevitable that local overpopulations will occur in regions with a high density of life-friendly planets or where civilizations expand particularly quickly. These overpopulations can be caused by various factors, but the availability of resources is paramount. In regions of the galaxy where metals are abundant, civilizations are likely to quickly acquire the capability to journey to the next star, rather than stagnate on a single one for millennia or even tens of millennia, risking the cessation of star hopping. Resources such as water, minerals, and energy sources are unsurprisingly crucial for survival and expansion. In a star system lacking habitable terrestrial planets or available water, advanced technologies could enable colonists to settle on ice moons, asteroids, and comets to extract water. Initially, suitable celestial bodies would need to be identified and thoroughly analyzed by space probes and telescopes. Robots and spacecraft could then be deployed to mine ice and convert it into water, which would be stored in special containers. Space stations or mobile bases could serve as central collection points and habitats, while underground or domed structures could be constructed on ice moons. Advanced water purification systems and sustainable energy sources like solar power plants or nuclear reactors would ensure the self-sufficiency of these settlements. Through these methods, a civilization could establish a stable and sustainable presence in space, even without relying on terrestrial planets. Yet, before we delve further into a hypothetical lifestyle with its enticements and perils, we must acknowledge that proximity to other civilizations is of paramount importance. When multiple colonies exist in relative closeness, their interactions could catalyze faster cultural and technological development, thus accelerating expansion. These interactions could encompass trade, knowledge exchange, and even alliances, which would favor the settlement of certain regions. Trade could involve the exchange of resources, technologies, and goods, thereby fostering economic stability and growth among the colonies. Knowledge exchange might occur through joint research projects and scientific collaborations, speeding up innovations and technological advancements. Moreover, closer cooperation between colonies could promote cultural understanding and social cohesion, leading to a more harmonious and stable society. Ecological and geological factors could favor the settlement of certain regions, as systems with habitable planets or moons offer a greater diversity of resources. Long-term perspectives might include the development of advanced propulsion technologies and new colonization techniques to enable expansion into more distant regions of the galaxy. Overall, The combination of these factors would lead to a diversified distribution of inhabited planets and colonies, with dense clusters of life and activity in certain areas and largely untouched regions as future expansion targets. Within a few 100,000 years, or a few million years, nearly the entire Milky Way could be settled through a complex network of colonies and trade routes, leading to a thriving and diverse galactic community. Another aspect to consider is the distance from already settled systems. Further a planet lies from a settled system, the more challenging and resource-intensive it becomes to reach and colonize. These logistical challenges could result in certain parts of the galaxy remaining uncolonized for a long time or possibly forever. Besides the logistical hurdles, the risks and uncertainties of interstellar travel also play a crucial role in the decision to explore distant and potentially life-hostile regions. These risks include not only technical and physical challenges, but also the possibility of encountering unknown and potentially dangerous conditions that are unpredictable from afar. This scenario would result in a mosaic-like pattern of civilization distribution within the Milky Way. One can only anticipate the emergence of a ring of inhabited star systems encircling the entire galaxy, representing the galactic habitable zone. The spiral arms would become the preferred settlement areas, whereas the core and bulge of the Milky Way would be accessible only through significant efforts. In these central regions, the largest and most active stars are found, whose massive size and short lifespans could pose a threat to neighboring systems, making settlement there unprofitable and life-threatening. In contrast, the spiral arms of the galaxy offer a more stable environment with fewer extreme stars, making them ideal settlement locations. It is expected that civilizations would settle relatively evenly along the spiral arms, leading to a galactic equilibrium, with an uninhabited bulge and center, as well as a sparsely populated halo, where stars are far apart and possess low metallicity, rendering them less attractive for the establishment of civilizations. Examining this mosaic-like pattern in detail, it further refines due to the distinct physical and chemical properties of the galaxy. Regions around the galactic core and bulge, characterized by dense star concentrations and frequent supernova explosions, would be marked by intense radiation fields, significantly complicating the formation and survival of complex life. These areas would be habitable only through the most advanced technologies and substantial efforts, greatly reducing the settlement pressure on these regions. Simultaneously, the spiral arms, known for their expansive, less dense star fields and overall calmer environment, have a greater chance of producing life-friendly planets. These regions could offer stable orbits and moderate conditions that favor the development and maintenance of life. Apart from physical conditions, gravitational effects play a crucial role in the colonization of the galaxy. The spiral arms experience fewer gravitational interferences from nearby massive stars, promoting the stability of planetary orbits and increasing the likelihood of long-term habitable zones. These stable conditions could lead to a higher density of habitable planets, thereby enhancing the attractiveness of these regions for settlers. Additionally, the spiral arms provide access to a variety of resources, including potential utilization of asteroid fields and gas giants rich in useful materials. Moreover, the structure and dynamics of the spiral arms could facilitate the formation of trade routes and communication networks, fostering interstellar collaboration and cultural exchange. This would further support the development of civilizations in these areas, enabling a denser and more interconnected settlement. The central regions of the galaxy, characterized by intense gravitational fields and high star densities, might be less appealing for establishing such networks due to the less stable and predictable conditions. In addition to physical and gravitational factors, the chemical composition of galactic regions would play an important role in settlement. Stars in the outer areas, particularly in the halo of the galaxy, often exhibit lower metallicity, restricting planet formation and the availability of essential elements. Those chemical limitations would further complicate the settlement of these regions, making them less attractive for civilizations dependent on specific raw materials. However, the interplay of these various factors, physical conditions, gravitational stability, resource availability, and chemical composition, would result in a complex and diverse pattern of settlement within the Milky Way. While the spiral arms might be densely populated and well connected, the central and outer regions of the galaxy would likely remain largely uninhabited. Unless technological breakthroughs enable settlement under extreme conditions. This nuanced pattern would portray the Milky Way as a galaxy with strong regional differences in the distribution of life and civilizations, while the spiral arms serving as the main hubs of galactic activity. The concept of galactic colonization through star hopping is not only intriguing, but also remarkably astute. Instead of relying on advanced technologies like warp drives, we could harness the natural movements of stars to expand throughout the Milky Way. This implies that we may not need to travel as far as we might think to reach new worlds. This approach demonstrates that significant progress can be made with relatively simple means and a thorough understanding of stellar dynamics. Undoubtedly, this requires extensive planning and the ability to manage resources and knowledge across multiple generations. Despite the many advantages, there are also several challenges and risks. For instance, unpredictable stellar movements or hazardous radiation zones could pose threats. Additionally, the fragmentation of civilizations, if stars continue to drift and colonies become isolated, could lead to communication issues. These potential dangers mean that we must constantly adapt to new circumstances and develop protective measures. However, even with these challenges, star hopping offers a realistic and resource-efficient way to colonize the Milky Way. At the end of the day, star hopping could present humanity with a novel path for expansion and space exploration. It is an intriguing alternative to the highly advanced and often speculative concepts of science fiction. By utilizing the natural movements of stars and strategically placing our settlements, we could develop a sustainable and efficient method for galactic colonization. This could not only enhance our understanding of the universe, but also lay the foundation for an interstellar civilization that exists in harmony with the dynamic processes of the Milky Way. Who knows, perhaps we will soon find that we are no longer alone in our corner of the cosmos.